Hey, welcome everybody to part 2 of the lesson on 6.6. This is all about logarithms, and in the last video we got to take a look at, what are they, and a little bit about how they work, how we can evaluate them. Now we're going to learn some of the properties about logarithms, and we are going to compare these to their inverse, an exponential, meaning we're going to look at properties of exponents to help us not necessarily prove or justify, but to draw a connection between these properties. So let's look at the first of 3 that we're going to take a look at. On the screen right now, you can see that we have the exponent property, that when you are multiplying like bases, you are permitted to take those two powers and add them together. We've seen this many times. The property for logarithms says if you have a product, as the argument of a log, meaning like you're taking the log of m times n, you can rewrite it as 2 separate logarithms, and each of the factors of that product become the argument in this sum. So what we have going on, and why we're comparing these, is here we have multiplication sort of becoming addition. It's not becoming addition, but it is, through the use of this property, we're able to take a multiplication problem and use addition to help us. And we can do the same thing with the logarithms. What's notable about it is here we have 2 separate bases being multiplied, and it turns into a single base being added, and it's backwards for logarithms. Here we have a single logarithm being multiplied, turning into 2 logarithms being added. And the reason for this is because they're inverses. A practical example of how this might be done is if you have, log of 3x, and 3x is the argument of that log, we are permitted to turn it into log of 3 plus log of x. Now, this may also work with numbers, so we may also have something like, the log of 20, which, by the way, we know is 5 times 4. We can turn this into log of 5 plus log of 4. All right, the next property worth talking about is basically the same one from exponents, except this time division and subtraction instead of multiplication and addition. Here, if we have the same base being divided, the operation is this yellow division bar or fraction bar. If we have the same base being divided, we can simply subtract their exponents. Well, for logarithms, if we have a single log with the argument as a quotient, we can take the numerator and denominator, make them the arguments of separate logs, and then slap a subtraction sign in between them. So the same kind of deal of division turning into subtraction. Here we have division turning into subtraction. And like with multiplication and addition, here we have 2 bases turning into 1. Here we have 1 logarithm turning into 2. Practical example of this could be something like, if we have a log of x over y, we can turn that into log x minus log y. If I force myself to come up with an example with numbers, I could say something like, log of 2, which I might choose to, I'm not exactly sure why I would do this, but if needed, I could break this up into log of, let's say, 6 over 3, turn it into a quotient, and that would become log 6 minus log 3. We're allowed to do this. That doesn't always mean it's going to help us out and get us to a nicer answer. Obviously, log 2 is going to be a more simplified version of what we want here. I should probably also note that these properties will work in reverse as well, so maybe it's more likely that we start the other way around. We might start with log 6 minus log 3 and then turn it into a quotient of a single log. So log of 6 over 3, which then can just become log of 2. Now, our final of these three properties that we're going to look at right now is probably the most useful, but it's also the one that we can't, it's the hardest to draw a connection between its exponential equivalent. We know that when we raise powers to powers, we would multiply those powers. Okay, so base raised to the m and then raised to the n, we can turn that into x raised to the m times n. So exponentiation, which doesn't really have a symbol, turns into multiplication. Well, we have the same kind of thing going here. We have x raised to the n as the argument of a log, and we are going to be able to turn it into multiplication. And what basically happens is this n kind of comes down to the front as a coefficient, and there we have n times log of just x. A practical example is probably what you would think. I mean, I could take the same exact problem, but slap a power on there. Log of x cubed can be turned into 3 times the log of x. And then potentially with numbers, if I had log of 4 to the 7th power, I could bring that 7 down as a coefficient 7 times the log of 4. Similarly, if it helps us out, we can also take something like 7 times the log of 4 and bring that 7 up to the power of the argument. And through the course of the few examples that we're going to see on the next few pages, we'll get to see how it can help us and how it could actually make things more complicated. We'll have to choose which properties of these to use, and then whether we're going sort of forwards or backwards. Are we going from something like on the left side to something on the right, or the other way around? All right, so back to our notes. At the top of this page, we do have those same properties that we talked about expressed now in all together in a table. And they have not changed aside from, I think, the letters in the logarithms are A's and B's instead of M's and N's. But what I do want to draw your attention to is what I have boxed over here, and that is that these are going to work for any base. So whether we have the common log, like the examples that we've seen, the natural log, or log base 2, log base 3, log base 4, it's all going to work. Just if you are combining logs, like with addition or subtraction into multiplication or division, we need to have the same base. And if we're breaking them up, so from this left side to the right side, then you're going to want to create two different logarithms with the same base. The base is not going to change. We're not going to add it. We're not going to subtract it, multiply it, anything like that. So I think we're going to do example 6 together because it says to apply the properties of logarithms. It doesn't tell us to make these better or more simple. It doesn't tell us to expand them, and the directions you'll have on anything that's going to be actually assessed are going to be much more clear. For these, we're just trying to see what we can do. So as an example, example 6, letter A, log base 2 of 8x squared. Now in this problem, we do have a product. So what this is asking us to do, or what we can do, is we can separate the 8 and the x squared as two separate factors, using the property that says multiplication inside of a log, like we have, can be changed into the addition of two separate logs. And once again, the two factors in the argument are 8 and then x squared. And that is one way that we can break this guy up. The reason we may choose to do this is because, well, log base 2 of 8, and again, we might not be there yet where we're super fluent in this, that's 3. It's asking 2 to what power is equal to 8, and that value is going to be 3. So we can simplify to 3. And then another thing that we can do with that second term is we can bring this 2 as a power down as a coefficient. So we can change that into 2 log base 2 of x. In example B, we have two separate logarithms being added, and we can do that same property but in reverse. So these are the two arguments, and we do have the same base, log base 8. We can combine those and make a log base 8 of 4 times 16. Now, we don't need to leave it as 4 times 16. We can make 4 times 16 equal to 64, which it is. And then 8 to what power is equal to 64? Well, that's going to have to be 2. In example C, we have log base 3 of x over 81. And since we have a division inside the argument of our log, we can rewrite this as log base 3 of x minus log base 3 of 81. And again, if there's anything more that we can do, we're going to try it. Log base 3 of x is not going to change, but 3 to what power gives me 81? That's going to be the 4th power of 3 is 81. In example D, we see, again, this in reverse. We have subtraction between two logs of the same base, so we can put this together as log base 4, and then there should be division, 32 divided by 2, inside that argument. Again, 32 divided by 2 can be simplified to 16, and 4 to the 2nd power is 16. And we can simplify that whole thing to 2 as well. So there are going to be times where we have something like C, where there's nothing we can do as it is, but if we break it up, then one of the terms will simplify, and that could make things nicer for us. There are also times when we can't simplify log base 4 of 32 or log base 4 of 2, but if we rewrite it as a quotient with a single log, then it'll simplify and give us something nice. Some of it is intuition, some of it is practice, experience, and sometimes just trying things and see what happens. For the last 3 on this page, they're going to ask us to use that power, that exponent property. So what we're allowed to do is take, if the x cubed is the argument of the log, I'm allowed to take that 3 and make it a coefficient, 3 times log base 5 of x. Now, unfortunately, that's all we can do here, but sometimes this is going to make the problem easier for us to work with, like in example F. I don't know what 4 to the 6th power is. I imagine it's a pretty large number. But if I use that same property and take that 6, bring it down to the front as a coefficient, 6 times log base 2 of 4. Now, I can simplify log base 2 of 4 to be 2. 2 to the 2nd power is 4. And then 6 times 2 is 12, and that simplifies really nicely. Similarly, we can do this process in reverse. In example G, I have no idea what log base 4 of 8 is, but if I take this 2 and now go in reverse, make it log base 4 of 8 squared, well, then I can simplify 8 squared to be 64, and then log base 4 of 64 is 3. 4 to the 3rd power is 64. If we look at the next 2 pages, example 7 and then example 8, they have more constructive directions. Example 7, write as a single logarithm. So we're going to be trying to take multiple logs as separate terms and bring them together so that the answer is just a single logarithm. In example 8, it says to expand the logarithm. Here we have just a single, and we're going to try to expand it as much as possible. And if along the way anything simplifies, we will. So if we do get a certain log that can turn into just a single number, let's do it. I think I'll do one from each section just to illustrate what we're looking for. And then these are the ones I'll turn you loose on. So let's start with example. Let's go with 7a. And in this one, if we're going to write this as a single logarithm, one thing that I'm not permitted to do is, even though these are the same logs, I do have this 2 hanging out in the front. And if I were to take the argument and divide them, like x divided by 7, where's that 2 go? Is it on the outside of my new singular log, or does it become a half? Or rather than do that, when you have something like this, they have to be just solo logs, meaning no coefficient in front of them. But we have a way to get rid of the coefficient. I'm going to take that 2, bring it up to the top of the 7, and make temporarily this log base 3 of x minus log base 3 of 49. And I don't know if you caught that, but I brought the 2 to the power of 7. 7 squared is 49. And now that we just have logs, no coefficients, I will employ that property that says if there's subtraction between them, we can make it division inside. So log base 3 of x over 49 will do. And whenever there's a fraction, not whenever there's a fraction, but often when there's a fraction, I'll put it in parentheses to really drive home what the argument is. If we're expanding, like in example 8a, well, I want to go exactly in reverse. So I'm going to say that if we have log base 3 of 9x to the 5th, I can first identify that 9 and x to the 5th are my 2 factors in that multiplication. That means I'm going to have a log base 3 plus another log base 3 where the arguments are 9 and x to the 5th. Now, since we are expanding these, or anytime really, is there anything that I can do to simplify? And log base 3 of 9 should be 2, because 3 squared is 9. And we can also take this 5 power and bring it down as a coefficient. It's not perfectly clear by the directions, but if the directions say to expand, also bring down your powers. All right, so take a couple of minutes, pause the video, and complete the rest from examples 7 and 8. I will show the answers on the screen momentarily. So make sure you pause the video and actually try them. And then, of course, you'll have the answers to look at. And if you have any questions, make sure you jot them down and we can talk about them during class. As we look at example 9, this is a style of problem that I've seen in a few different textbooks, including ours. It's a way that you can get around needing a calculator to answer questions. So since you're going to see these types of problems, I thought I'd bring some up, and example 9 is that problem. So they give you 2 facts. Log base 2 of 3 is 1.585. This is true, but even if it wasn't, you can still run with it. And log base 2 of 7 is equal to, or is approximately equal to, 2.807. Both of these, of course, have been rounded. I neglected to say that with the first one. You can do this even if it wasn't log base 2, like maybe it was log base A and it was just an arbitrary value. The reason that we're doing these is to indicate that we can get a value knowing partial information about these logarithms. And we're going to use the properties that we just learned to evaluate them. So in example A, we have log base 2 of 3/7, and I think without knowing any of the properties, you would be tempted to divide those 2 decimals. But we know better. We know that if we are dividing the argument of a logarithm like this, we'll rewrite it as log base 2 of 3 minus log base 2 of 7. And then what we can do is just kind of replace or substitute the values that were given to us. Log base 2 of 3 is 1.585. Log base 2 of 7 is 2.807. And if we were to subtract those, 2 is a larger number. We're subtracting it, so it's going to be negative. Turns out this one will simplify to negative 1.222. Now, that one's nice because you see the 3 and you see the 7 in the problem. In example B, you may be tempted to think log base 2 of 21, there's no possible way to simplify that. But because we can factor 21 into 3 and 7, we can make this work. So I can replace 21 with 3 times 7. And then using the property, we can rewrite as a sum and then replace the values of log base 2 of 3 and 7. Now when we add these, we're going to get 4.392, which will be the value of log base 2 of 21. When it comes to log base 2 of 49 in the last problem, there's really 2 ways we can reason this one out. I think what they wanted us to do is recognize that 49 is 7 squared. So if I break this, or if I rewrite this as log base 2 of 7 squared, I can bring that power 2 down as a coefficient. It would be 2 times log base 2 of 7, and then I can replace log base 2 of 7 with the decimal given to us. It would be 2 times 2.807. Now, likewise, you can also simplify it as like log base 2 of 7 times 7. It's what 7 squared is anyway, but if you do it this way, it turns into an addition problem. So it's going to look a lot like this step here, except both terms are going to be log base 2 of 7. So in this case, we would have 2.807. I'll write it out. And then obviously mathematically, the way it's going to work out is whether we're multiplying 2.807 by 2, or if we're adding 2.807 to 2.807, we're going to get 5.614, which is of course the same value. Now, the change of base formula, our last topic for this section, it's got to be one of my favorite of all time formulas. And the reason is it kind of works for any number that we have. So if I take like log base 78 of, and again, I'm drawing numbers, I'm pulling them out of the air. The first numbers that I see 361. It would be really, really tough to come up with a nice approximation of what this value is. However, we can always re-express this as a logarithm with the base of our choosing. It's wild to me that this works, and I've seen how it works, but I'm impressed anyway. But we can take any log of any base with any argument and rewrite it as a fraction with whatever base we want. So if I want the base to be, do I have any other numbers? I see 9. I can rewrite it as log base 9, as long as it's in the following format. And log of any base you want, top and bottom, and the arguments are going to be the 361, the original argument, and then the 78, the original base, becomes the argument in the denominator. Okay? Now, this doesn't really help us in this case. So how is it actually useful? Well, instead of using log base 9, I'm going to use the common log base 10. Well, I'm not going to write the 10, but I could put a common log in my numerator and denominator, leave the 361 as the argument of the top, make the 78 the argument of the bottom, and this is much better. Why? Because we have calculator buttons that'll allow us to do this. So if I type in log of 361, this is one case where that habit of closing your parentheses is going to help. we must close the parentheses before we divide by the log of 78. But now I have a value, 1.3517. Now, these calculators do have a way to type in a log of any base. I'm not sure how it's going to show up on this emulator, but if I hit the math button, I always say, aren't they all math buttons? But here we are. We get this list here, and on mine, again, it's going to look slightly different than the TI-84, but it's meant to model it. Option A here is log base. On the TI-84, it should look the same, but if I choose that option on the calculator, and depending on which model you have, like the newest TI-84 with the backlit screen or an older one, they can both do it, just the formatting is going to look a little different. This one actually gives me subscript of 78 and a argument of 361. I can compare to make sure that it works. And what do you know? I get the same value out to all the places that are visible. Now, what else could I have done? I suppose I could have used the natural log. And as long as I maintain that 361 is the argument of the numerator and 78 is the argument of the denominator, according to this property, this should work out as well. So the natural log of 361 divided by the natural log of 78. Again, same value, as you can see. So what are the downsides? What are the cautions? And actually, what are the upsides? I think the fact that this theorem exists, or this property exists, allows us to access these weird logs just from the buttons that are actually on the front of your calculator. You have the log and the natural log button there. Downsides. If you type it in wrong, you're going to get the wrong answer. Watch as I type in the natural log of 361, intentionally now forgetting the parentheses and dividing by the natural log of 78. Now this is a wildly different value. How is my calculator interpreting that? It's saying the natural log of 361 over the natural log of 78. Okay, that's not what we wanted to calculate. So you have to pay attention to your parentheses. You have to pay attention to like the order of operations there. It actually doesn't matter if we finish the 78 or the parentheses after the 78. That it's going to fill that in automatically for you. It's going to close any parentheses that you leave open. But if you needed to close one, that's got to be on you. All right, so here is that change of base formula in notation format. It looks more complicated than it is. Remember, you can choose any base that you want to convert it to. That's the value of C here. And you just have to make sure the M and the B go where they're supposed to be. Why are they those letters? I don't know. It's just the way they are. So looking at example 10, we're going to be able to do some of these by choosing our base strategically. Okay, example 10a here, log base 81 of 27. The first thing that I notice when I see this, and it's because I've taught this class, 81 and 27 are both powers of 3. So if I choose 3 as my common base, I can rewrite this as log base 3 on the top and the bottom, making the 27 the argument of the numerator, 81 the argument of the denominator, and this I can do without a calculator. This one, log base 3 of 27 is going to just be 3, because 3 cubed gives me 27. And the denominator is going to be 4, because 3 to the 4th power is 81. And my answer is 3/4. Now, if I want to use a calculator, it probably makes more sense to change these into either natural logs or common logs. I think most students like to write log because it looks more familiar. I like natural log because it's one less letter. But the natural log of 27 over the natural log of 81. And on the calculator, that natural log of 27 divided by the natural log of 81, here we go, is not approximately, but exactly 0.75. Well, that's what 3/4 is. So if you get a value that's rational, meaning terminating or repeating, maybe there's an easier way to do it. Okay? And what you'll try to do for some of these is decide which ones can you do without a calculator. So even just comparing C and D, do either of those values in a problem, so 5 and 36 or 216 and 36, do they come from a common base? And for C, no. I can't raise a power and get both 5 and 36. But in D, I can raise 6 to two different powers and get both 216 and 36. So in letter C, I will need a calculator. And then I'll say over here, we do not need a calculator. So let's do them. In example C, I like the natural log, but for your guys' sake, I will also show you that the common log works. Original argument goes in the numerator. Common log on the bottom as well. Original base goes in the denominator. And we'll have to calculate it. So the common log of 36 divided by the common log of 5. It's approximately 2.2266. And I'll get rid of the calculator because example D, I can rewrite with that base 6 that we talked about. So I'm going to say log base 6 of 36, log base 6 of 216, and on the top, we're going to get a 2. On the bottom, we're going to get a 3, right? 6 squared is 36, and 6 cubed is 216. So 2/3 is going to be my answer. All right, so I'll ask you to do the same with these. With example E, F, G, and H. If you could do them without a calculator, do them. If not, use the calculator and round to, let's say, 4 places. All right, and your answers are as follows. And it looks like examples E, F, and H all required the use of a calculator, and G was able to be done by using the base 2. Both 8 and 32 are powers of 2. So it comes in handy to know what your bases are. It comes in handy to know what your powers are for a lot of values. A lot of students may make the mistake of thinking like example F and H might be able to be rewritten and done without a calculator, but it's different than reducing a fraction. It's not, oh, 4 and 18 are both even, therefore it's going to work. Or 2 and 300 are both even. They would both have to be powers of the same value. Now, if that 300 in letter H, if that was a 128, a power of 2, yeah, we're in good shape because both 2 to the first power and 2 to the, I forget what I said, 2 to the 7th power is 128. Those would get us to a solution. But if they're not in the right set of numbers, we are just going to have to do them using a calculator, and we should probably round to 3 or 4 places. So check if you're unsure. All right, so with that in mind, we have come to the end of the lesson, and it is now time to do some extra practice, some independent practice with the homework. And if you completed questions 1 through 18 after watching the previous video, you should be part of the way done. You may proceed from here and go ahead and complete the rest of it. And if you have any questions, as always, jot them down and ask about them next time we're together. Catch you in the next one.